Hello, and it's now day 13 of the Electronic Sound Advent Calendar, and I want to see what I'm going to add today. Where's 13? There's 13. And what have we got in there? Ooh, this is exciting. Got some kind of chip here. Okay, I think we have a look in the book and see what this is all about, because this is exciting. So, day 13. So behind the 13th door, you'll find a pre-programmed sound processor. Cool. Soldered onto a small circuit board. Okay, so fair enough. Where its pins are numbered like those of an IC. So it's kind of like an SOIC, I suppose, or something like that. And it's been just broken out. 120. Right, that's nice. So mount it on the breadboard and wire the circuit is shown. Right, so we're going to have to change our wiring a little bit. Oh, pin 7 of the processor must always be connected to contact row Y and the other one to contact row X. So, oh, I see. That's just making sure you always have the positive and negative the right way around. On every day, batteries must not be inserted until it's completely assembled. Yeah, fair enough. Although I have been leaving them like this while it's not actually connecting the ground of the battery to anything. But yeah, we'll disconnect them completely for this case. Right, so we got some fair chunk of rewiring to do. Let's take this away, and I think we have to take that away, and we'll have to add that back in somehow because I still like to have that button. There might not be enough room for it, so that stays there. That capacitor comes out and we display this one back. Okay, so it's only one day that it wasn't quite displayed. Wait a second, make sure I'm not connecting to the wrong pin. There we go. Alright, so we move those. Now, that capacitor goes there. Okay, but we're also going to need 2 more of these jumpers. So let's make those. So my jumper making kit. And I think the wire, I left it in slot 5. There we go. And we'll make it about this long. So cut one and cut another. Now, while I'm cutting, it points out that important changes to the previous circuit include the 100 nanofarad capacitor now between pin 9 and ground, contact row Y. Every time it says that, think ground, ground. As well as the wire jumper between pin 10 and Y. Okay, sure. It adopts the function of the previous push button and switches rhythmically between the 2 frequencies. So it's doing this point what that button we were doing when I was going dee. Okay, right, well, we'll see. Now I'm just going to take some insulation off. We found it's still not, so I'm going to go down to there just to get the insulation off of these jumpers I've created. There we go, there's one. Do the other in the same way. Okay, we've got another jumper. I'm just going to also pre-shape it. And there's one. That's terribly pre-shaped, actually. What I don't want to do is lose it, but look, that's not very even, is it? Let's try and make a better job of the next one. Don't think it'll matter too much, honestly, because the shape of these is not what's going to count. It's just making my life slightly easier when I've got to poke them into the breadboard. Okay, here we go. That one's far better. Right, let's move this aside. I'm going to put up here as a reference. Now, what they aren't saying is what this mystery chip is. I was hoping they would tell us. Oh. I think we're going to get that under the microscope a bit later to see what's really going on. But we'll build it first. Going to use these as makeshift giant tweezers. Okay, so this is here. Oh, that didn't quite go in. One side doesn't want to go in, and you find this from time to time with these some breadboards, unless you get the nice ones. I think the actual answer is to change these ever so slightly with the pliers so they're splayed downwards instead of out, so then they're not kind of pushing at slightly different angles. There we go, that's in, that's it. Pop this out. So I'm ever so slightly wary that there's not quite enough on one end of this. So I'm going to just curve that round because I am slightly worried it won't go all the way in on one side and would lead to poor contact with something with the ground. And ground issues are an easy way to have problems in your circuit, especially if it's something that's not quite contacting but looks like it's in. Like we saw with a capacitor a couple of days back. Well, actually it was yesterday with the oscilloscope. We knocked the capacitor leg out and it just stopped doing anything. So this chip goes in this way up. And okay, so one above, two below. Right, fine. So there's your two below, there's your one above. And this wire goes to row 5. There's row 5. You can just about make out, if you look closely, the 5 that's embossed on that. And I'm actually wondering if that should be the shorter length. Okay, let's make that the shorter length so I can do the longer length here. Round to this pin here. And I am going to follow their routing because their routing kind of keeps things tidy, but okay, it's going to have to go over the top because it's just a little bit on the short side. There we go. Okay. That will do. And 5 in the middle there. Going to use my pliers just to nudge that in. You see, one thing to know about these X and Y, as in the live and ground, or positive and negative, is this whole rail is the same. So anywhere along here, it doesn't matter. And the same with that rail, that one is the same. So everything along there is positive and everything along here is negative. So if you move one along, it doesn't matter. Obviously, you need to make sure you line up with the pins very clearly on the chip, or the chip will malfunction, or you'll blow it up. So you have to make sure those are aligned perfectly, or at least aligned correctly. Right, so none of the top here is changing. We got our capacitor, got the resistors there, we got this pin in the middle. These two capacitors are lined up there. Good, okay, they're tucked in properly. So this time I'm being a bit more careful to check because I don't want to damage what is really not a very replaceable chip. We don't really now have a good place to put the button, the extra button that I added. So I'll ponder that because it was nice when we had that. These two rows up here are empty. I could take those rows up here. Pin 7 must be connected and pin 9 to row. Oh, pin 9, yeah, is connected up there. Okay, so this capacitor I think is a bypass capacitor for, as in to make sure we don't get any noise out of this chip and the rest of the circuit. Also, it's not messing with the ground, I see. So that one isn't so much a timing function as a dampening function. So that's connected directly between the positive and negative. Let's just get rid of this. And with that cable there, I can then still have my switch, but in a slightly different place. So put it up here. Needs to be the other way up. Will it go in the other way up? Yeah, it will. There we go. Put this here. That doesn't appear to be doing anything. What have we got going wrong there? So that's up to the voltage. We've got this pin here. This is where the oscilloscope might be nice to see what's coming out of this pin, if it's doing anything. Got 10 is ground. We've got pin 6 is also on ground. Is that what that is? Pin 6? No, 9, 8, 7. That is pin 7. That's right. Okay, so pin 7 and pin 10 are grounded. Pin 9 is up to here with bypass capacitor. Oh, wait a minute. I've not really pushed that all the way in. Oh. Still doesn't really do what I want it to do. Let's try and connect it without the button. So why having it here and there is different? Okay, it is working. But what was strange about that, is that pin is going to there. There is no good place because that pin actually connects to this pin. Oh, let's not let that accident contact anything. That goes through this pin of the potentiometer, so it changes everything. So there is no good place to put the switch. Shame. Or I've not found it yet anyway. So there we go, look. And what's going to be happening is it's going to be pulling this down to ground from wherever it is up here. And we'll make sure those don't touch. There we go. Okay, so we do have a sound processor doing something. At least they call it a sound processor. I think it's just a timer that is pulling one pin down to ground repeatedly. Some simple clock frequency. I hope you have enjoyed this video. I hope to see you for the next day's Advent, and maybe I will get this under an oscilloscope, excuse me. I'll get this under a microscope, although an oscilloscope might be interesting to see that other signal, but I think it's going to be a square wave pulling it down to ground. Actually, it might be a square wave modulated with whatever's going through here, so we'll probably just see the two square waves with a frequency change. We see we've got is, was it a Nuvoton, and is it MS51FB9AE? Don't know what that is. I'm assuming it's some kind of programmable ROM or programmable logic. So this is interesting. I typed in this Nuvoton MS51 business, and straight away I could see stuff about it. Here's the product. 8-bit 8051. So maybe there's an 8051 with some ROM already on board or something pre-programmed. You've got some memory, on-chip RAM, MS51. This is the same device. So an 8051, it's a microcontroller that's programmable. It's fairly common and I suppose of a particular vintage. So I think they're at least 20 years old, if not more, if not way more, because I think I was looking at these even 20 years ago and they were oldish then. And so we've got analog interface here. We've got UR SPI and I2C.
general purpose I/O, some clock control, power control. It's a fairly capable looking device. TSOP 20, which I suppose is what that little package is. LED lighting, home appliances, industrial, motor control, battery management, power supplies. Fair enough. 8051 base CMOS microcontroller running up to 24 megahertz. A 16K flash, configurable. LD-ROM. I'm not sure what LD-ROM is about, but user developed boot code, which might be what's running on this. 1K SRAM, 256 bytes of on-chip RAM, so I guess that's just your registers. Flash memory in pages of 128 bytes. External clock input, internal oscillators, which is probably we're using an internal oscillator for it to do the up-down noise we're hearing now. 10 kilohertz low speed, maybe it's that one. 10 kilohertz. We don't need megahertz for this. Multiple timers. I mean, this thing is actually reasonably capable. That's actually quite an interesting little find. So there we go. We found out that we got an 8051 on our little electronic sound advent calendar board. I wonder what these cost. Do we have a cost in this line here? We don't. Its status is in mass production. Let's see if we can find out about buying these. 32 cents plus tax, but that's for one-offs. Oh, look, DigiKey has them. There we go. We don't need to type buy. We just click on DigiKey. Okay, so 82 pence for those, 73 pence for those. We get to 100, 57. So those are 57 pence each in hundreds. Thousands, these are now 37 pence each. So 37 pence for a reasonably capable microcontroller. I can see why a manufacturer might choose these for mass production.
Go make stuff and be awesome. Bye.